Hi, my name is Victoria Vargas, and this is our Engineering 1330 Computational Thinking and Data Science Instrument Calibration Project. We are group 14. Our members are Megan, Mariah, and me, Victoria Vargas. So a little bit of background information, some research. We were collaborating two pressure measurement systems. So this project focuses on collaborating two pressure measurement systems, an analog gauge and pressure transducer. So during collaboration, deadweight testbed is used to generate known reference pressures. So this device applies precise pressure using calibrated weights on a piston. The resulting pressure is considered the true value. So each sensor responds to the known pressures, the analog gauge, which gives a direct pressure reading, and the pressure transducer, which outputs a voltage. So we're working with those two pressures. And our overall goal of our project was to develop accurate collaborated tools for interpreting sensor data and ensuring reliable pressure measurement with real-world data like true engineers. So applying whatever true data, real-world data might be going on in an engineering environment and being able to transcribe that data. So our first step in our project is we wanted to import all of our libraries used, so our NumPy, Pandas, Matplotlib, Seaborn, and finally our libraries that were used for our models using libraries. So that's what we see in this column here. And exploratory data analysis. So the first thing we wanted to do is reform the column headings. Megan was able to do this for us. We renamed the columns to make the data easier to read and overall look back at later and use our, and make it overall easier to compare. So that's what we did here. We read and renamed the overall Excel data column, and we overall saved it as a new file called sensor data. And here is us changing those title names to be a little bit more clear and easier to read. And for some general information, here is our overall info to describe our data column names, count, data types, and overall statistics. We wanted to have that on hand. And the next thing that was done by Megan is she was able to make a scatter plot between all the columns in the data set. So here is that scatter plot. And these plots actually show all the columns have a positive linear correlation between each other. So we really wanted to be able to define that relationship between the pressure and voltage and overall true pressure. We wanted to make sure that they have an overall relationship overall, that they have some sort of correlation here. They have a positive linear correlation. And in addition, Megan also did a correlation heat map. So here she computed all the correlation coefficients between all the columns in the dataset and displayed them as a heat map. So the heat map was able to show the same results as a pair point, with every correlation coefficient very close to 1. So again, this heat map was to check the sensor readings, voltage, and gauge, and have a strong linear relationship with true pressure, showing they are very reliable for calibration. So again, it's just ensuring, because those values are so close that the Seaborn's library rounds them to 1, because they are very close, they are very reliable for that collaboration. So Megan went ahead and she coded the linear model from scratch. So she made our model without using sklearn library. So the first thing she did is she copied the original data frame, and then she went ahead and plotted predicting voltage from true pressure. So she plotted voltage to true pressure, and there is that graph. The next thing she did is she wanted to build a code that manually builds a linear regression model to predict voltage from true pressure. Again, this is without using machine learning libraries. So the first thing she did is calculated the mean and standard deviation of both variables, and then computes the correlation coefficient between them. So that's what's going on in kernel number 91. And then she used the regression line formula, which is slope equals r times stdy over stdx. So it calculates the slope and intercept, and finally it defines a custom function to estimate voltage from pressure and adds a new column to the data set with these predicted voltage values. So that's what's going on down here. Here's the addition of the new column with those new predicted voltage values. And now that we have all this information, Megan was able to make a linear line regression to the original scatter plot to show the overall correlation between all those values and the overall slope. So there is the plot, and then appending the new column on standard data S of error between actual and predicted voltage. So next, she coded the error, also called residual, between the actual voltage readings and the predicted voltage just from the model. So it adds these new residuals as a column and then creates a residual plot, which shows how much basically each prediction differs from the real voltage. So there's a red horizontal line in the middle to help us visualize whether errors are evenly distributed above or below 0. So that would mean the model is well balanced and accurate. So as you can see, there is some plots points above the line and some below the line, and they're pretty well balanced. There's only one outlier. So as Megan explained at the bottom, there's no pattern in the residuals. The regression line predicts the voltage with the same level of accuracy across the entire range of the true pressures. So this overall can help us conclude that this model can in fact work well. So then next she was able to calculate the mean squared error and root mean squared error for the predicted voltages. So these values just show how far off the predictions are from the actual voltages readings on average. So usually a small RMSE usually means the model is very accurate. So that's what we have here. We have a small RMSE, so we can sort of predict that this model is in fact going to work well. And Megan was able to do the same exact thing, except now using predicting gauge pressure from true pressure. And so she was able to follow exactly the same steps, except now with gauge pressure. So that's what we have here. She plotted the point, and she was able to calculate the mean and overall slope and intercept to go ahead and get that regression line formula and apply that to a new column, which then she was able to plot that overall regression line to the original scatter plot, and then overall get our plotting error with an average of residual. So again, as we come down to this residual plot with zero line, because there's no pattern in the residuals, the regression line predicts the voltage with the same level of accuracy across the entire range. So again, we have this sort of model here showing how we have a regression line and that overall line. So we're looking at the points above that line and below that line because they're sort of on the same balance with the exception of the one main outlier at -10. We can also predict that this model is also going to work well. And calculating MSE and RMSE. Again, as we stated before, a low RMSE usually means that the model is going to be very accurate. Here, 1.16 is also going to be considered a low model, or a accurate model, sorry, because 1.16 is a low number. So now we have the linear model. So using sklearn library, this was my portion of the project. I was able to copy the original data frame and then plot the voltage from true pressure. So that's what I was able to do in these columns here. And the library I used is sklearn linear regression to overall make linear regressions and overall predict the voltage. So this code is able to build a regression model to predict the overall voltage to true pressure. So there is my regression line shown with the true original plot and then adding a new column in from, of course, the data that we had altered. And then now we have another plotting error residual plot with an average residual, always 0. So as an explanation of my plot, because there are no patterns in residuals, the regression line predicts the voltage with the same level of accuracy. Again, we have the sort of balance of points above and below 0. So that overall means that the model is going to work well because of that balance. And we have another low RMSE, specifically 0.0071. So that's a very low number, but again, that's what helps make a more accurate model is that lower number, RMSE. So then now I did the same exact thing, except now with gauge pressure from true pressure. So there is a model of these codes right here following the same exact steps, except for now with that gauge pressure. So again, coming down to the residual plot with 0 line after making the regression line from those libraries specifically used by me. Because there's no pattern in the residuals, the regression line predicts the voltage with the same level of accuracy across the entire range. So I can deduce that this model also is going to work well. And at the bottom, we also have another low RMSE, specifically of 1.16. So Mariah was able to do this part of the project. She did an assessment of the models and comparison of the results. So she made our uncertainty bracket function. So assessment of both models collaborated analog pressure gauge. So now this is the scenario we were given in the final project, and she was able to apply this from both linear regression model from scratch and of course the linear regression model with the library. So these are these codes right here. And finally, for the assessment and comparison at gauge pressure value 64 psi, she was able to confirm that both the linear regression model from scratch and with library yielded the same results. So this shows that both methods work effectively and result in the same estimated tire pressure. So they're able to actually get those same results. And if we actually look at the assessment of both models' collaborated pressure transducer, we would also find that she was able to come to the conclusion that both linear regression model from scratch and linear regression model with library yielded also the same results. So this shows that both methods work effectively and both estimated a true pressure from a pressure transducer reading a specific value, in this case voltage. So now we were able to apply this to some real data, real information that was being given to us, so projected pressure readings from a table. So Mariah decided to use, because both models are the same, it doesn't matter which one she used, so she decided to use the one that contained libraries because it was easier to apply those libraries than overall coding from scratch. So she was able to get these real values with She was able to get these real voltage values and pressure values and overall confidence level with this table of values given. And finally, function to make predictions using the model, build an interface to allow users to enter voltages. That's what she did here using that regression model with the library. She was able to make a float, and then any user is able to input a pressure transducer reading, and that is able to give you some results of a voltage reading and a pressure reading as well as a confidence level. And that is it for our final project. Thank you so much for listening and have a great day.